Section 2.5 is concerned with the calculation of atomic masses. So it's important to realize that the particles that make up atoms and atoms themselves have very small masses when their masses are expressed in grams. To get around this problem, chemists have developed a relative mass scale based on the atomic mass unit, or what we call AMUs. And 1 AMU is equal to 1.67 by 10 to the minus 24 grams. So on using this scale, the mass of a proton or neutron is about 1 AMU, and the mass of an electron is about 5.5 by 10 to the minus 5 AMU. So it's useful to think about where the AMU came from, and what chemists did was this. They assigned a mass of exactly 12 atomic mass units to the carbon atom that has a mass number of 12 and an atomic number of 6. This allows the relative atomic mass for any other atom to be computed as either a fraction or a multiple of this number. What we're really saying is that 1 AMU is 1/12 the mass of a carbon atom with a mass number of 12. Now, in the periodic table, we've already mentioned that the atomic number is listed above an element's symbol. Below an element symbol will be a number with a few digits after the decimal point. What this number represents is the average atomic mass that has been weighted to take into account all of the isotopes that are present in a natural sample of an element. So for example, boron is known to natural samples of boron are known to be made up of two isotopes, one with mass number 10, the other with mass number 11. The isotope with mass number 10 has a mass of around about 10 AMU, and that with mass number 11 has a mass of around about 11 AMU. The lighter isotope comprises about 20% of the atoms in a natural sample, and the heavier isotope about 80%. So when we calculate an average, taking into account these proportions, we would expect it to be closer to 11 than it is to 10. And that's exactly what we see. The weighted average that is given is 10.811 AMU. Now, I'll show you in a couple of slides how we go about calculating these weighted average atomic masses. So, we've seen that many elements exist as multiple isotopes, and those isotopes will have a characteristic abundance, what we call the natural abundance of the isotope. Normally it's represented by a percentage. Each isotope will have a mass associated with it, and then when we average these guys, taking into account the relative proportions of the isotopes, we'll get an average atomic mass that kind of represents what an average atom might weigh in a natural sample. This average atomic mass will always be closest in mass to our most abundant isotope. So for our three isotopes of hydrogen, 99.99% of the isotopes have atomic mass of 1.0078, and then there are a few heavier ones, so it makes sense that our average atomic mass is near 1.0078. If I go to oxygen, we can see that there are three isotopes. The isotope that has a mass of about 16 makes up most of an actual sample of oxygen, and then there is a small amount of some heavier isotopes, so it makes sense that the average atomic mass, taking into account these proportions, is a little bit heavier than the most abundant isotope. So how we calculate this weighted average is by taking the percent of each isotope dividing that by 100, and then multiplying that by the mass of the isotope. We do this for every isotope that's present, and then we add them together. Now you'll know if you've got the right answer because you can always look your answer up in the periodic table to confirm that you got it correct. So let's look at some examples now. So this problem reads, there are two naturally occurring isotopes of lithium, lithium-6 and lithium-7. Using the data below, calculate the average atomic mass of lithium. So we take the percentage of our first isotope, we divide that by 100, we multiply it by the mass of our first isotope, and then that completes the first isotope, and then we do that for the second isotope as well. We take the percentage, we divide by 100, and we times by the mass of the isotope. And when we put that into a calculator, we get the mass of an average lithium atom in AMU, and it should look like what the number is in the periodic table. So putting that into the calculator, and I got 6.94 AMU. If you compare that to the value in the periodic table, you'll see that it is very close, if not the same. So here's another one. This is a little bit more complicated because we've got three isotopes of oxygen here. We've got the masses are given, and then we've also got the percentages. So it's the same thing. We're going to take the percentage of the first isotope, divide that by 100, and then multiply that by the mass. We do that for every isotope, and we add them all together. And then the last isotope, and then when we average that, we end up with 16.00 AMU. Okay. So they're all kind of done the same, and you can always check your value in the periodic table. The answer that I've given there goes out to more digits, but if you round it off to 4, you get 16.00. So sometimes people ask, how do we measure the mass of an atom? Well, it's kind of interesting. What we do is we get our sample and we kind of vaporize it, and we get everything sort of floating around in space, and then we give our sample of matter a push, and the atoms travel along a long tube, and what we will find is that the light atoms or light particles, whatever our sample happens to be, will reach the end of the tube quicker than the heavier ones. And by measuring what we call the time of flight, how long it takes for a particle to travel our tube, we can relate that back to the mass of the particle. So, revisiting what a periodic table entry looks like, generally we'll have the symbol for the element in the middle. Above the symbol, we'll have the atomic number, which we give the abbreviation Z, and then below the symbol, we will have the average atomic mass. The average atomic mass. Take note that this is not the mass number. Don't confuse the average mass or the atomic mass with the mass number. They are different things. So here's an example. You can see that every element in the periodic table has a unique atomic number, and then underneath we have the average atomic mass. The mass number is generally not given in the periodic table. You need to calculate that. So let's have a look at this one. It says, what is the average mass of a tin atom in grams? The average atomic mass is found in the periodic table. Please use 2 decimal places. So let's go back and see if we can find the mass of tin. Tin is over here, 118.7 AMU. So 1 tin, 118.7 AMU. And so how much is that in grams? Well, 1.67 by 10 to the negative 24 grams for every 1 AMU. It's not going to be a very big number, is it? 118.7 times 1.67 by 10 to the minus 24. Put that into my calculator. To 2 decimal places, 1.98 by 10 to the negative 22 grams. And the reason I included this example was just for you guys to recognize that atoms are tiny. They really don't weigh very much at all. 10 to the negative 22 grams is a very small number. Okay, and that concludes the video on section 2.5.